So tonight, what I'd like to talk to you about is the formalism of the neutron current and some topics in neutron sources. So the neutron current, which is denoted with the J, and it's a function of position vector and energy. Its state space is four-dimensional, or it can also be time, five-dimensional. We can write this as a special type of integral. And the domain of the integral, and it's an integral of flux or that is the angular flux. And that angular flux is convoluted with the angle of the flux. And it's integrated in the special sort of integral with respect to solid angle of the hemisphere of the solid angle. Well, let me draw this out and maybe it'll make more sense. If I were to have, and the integral's a bit more complicated than this, I haven't finished writing out. If I were to have my unit sphere, and I divided this down the middle into two hemispheres, we have one hemisphere here and one hemisphere here. We'll denote this one H sub 1, and this guy here will denote H sub 2. Then the solid angle, the neutron current is equal to the difference between this integral here of this hemisphere and this integral here of the solid angle convoluted with the flux. Where this H2 here is this hemisphere here. So you can think of it as given a arbitrarily small unit sphere in space. If we take the flux here and multiply each point in flux phase space by that point in flux's phase space's direction vector, and we do that for all the direction vectors coming out here, and then we subtract all the direction vectors coming out here, then that gives us more of a formal definition of neutron flux, neutron current coming from neutron flux. Carl Ott uses a slightly different notation, which I find personally a bit confusing. He writes the neutron current, and then he has this integral here. Omega this integral here, where we have the direction vector, flux of that position, the angular flux of that position, omega, and then he subtracts, still within this parentheses here, phi of R E. Then he adds this minus sign here, negative omega, with respect to d omega. And where this H here, this denotes a single hemisphere. And this is kind of confusing to me because what you're doing is you're flipping the direction vector and then passing it into this probability density function, which pulls the negative out of the phase space. So that's in effect the other hemisphere. So that was really confusing to me, so I prefer to write it in this form here. So that's the formalism of neutron current. Now some things we can do with neutron current. We can find the number of neutrons passing through a surface. So for example, if we have this sort of arbitrary surface in space, I think they call this a type 1 surface because these are parallel. Not too sure. There was her first name was Susan. She wrote a book on vector calculus from MIT that this is mentioned in. So if we have this surface, capital S, surface capital S, and we have some sort of neutron current passing through this guy, like so. What we can write is that the current here, this is equal to the surface integral about S of your neutron current, J of R E, times, dotted with the differential surface element. Now, this dot product with the differential surface element, if you haven't seen this guy before, if we were to sort of zoom in on a very small element here, like this, if we have our normal vector, in here, and we were to have our current passing at some angle theta with respect to the normal vector, so this is J, and then we project J, we take the normal component of J, that is to say the projection of J onto N. This just equals the absolute magnitude of J times the cosine of our theta. You can work this out if you want. So when this ds here, this should be a vector. This is a vector element that represents the differential surface area of our surface here, a small, tiny surface element, and its magnitude is equal to the area of A, and its direction is equal to the direction of the normal. So the magnitude equals magnitude of, we can call it dA, and the direction equal to, just call this n hat for our normal vector. So we could rewrite this guy as an area integral of J, or current, times the cosine of our angle between this vector and this vector, normal vector and the current vector, times dA. So that is the number of neutrons passing through the surface. So the basic idea is you just add up all the little differential currents, and that gives you the total current expressed in as a fancy integral like this or this. The last thing I wanted to touch on had to do with if you use MCNP or something, the group current. Okay, and we just denote with this with a J with a subscript G, and it is a function of position only. If you use MCNP, you can have something like a surface tally or something that gives you the neutron flux, and this is just equal to the integral from some group boundary to another group boundary. Remember, if we discretize our energy groups with the zeroest fastest convention, so on and so forth, then if we want or actually I should use the different notation. Notation. So this is our Gth energy group neutron current. So the neutron current following into some energy band here. This is going to be fast, thermal, or some sort of other discretization method, so on and so forth. And this is just a way of getting the neutron current for a particular group. So that's the formalism of neutron current. The last thing I want to touch on is this idea of a neutron source. The neutron source, these are probability density functions, and the phase space is position vector, and it's also has a independent variable of energy, and all this represents is a source of neutrons. So if I have some sort of arbitrary volume in space, then we could have, for example, a independent neutron source, S of R E, for example, 1 MeV neutrons coming from this point here. This is a neutron source, and we just use the S notation here. And there's several types of neutron sources. There's independent neutron sources. This is notation for independent. Then we have the fission neutron source, which we denote as S sub F, or sometimes S sub FIS, and it's a function of position and energy. And once again, this energy here, this is pulling it, the energy pulling out of it. So for example, if we have a 1 MeV neutron source, and it's located here, if we were to draw a line across here and then plot that up here with respect to energy, let's say we hold this is R, and this is going to be our E here. So we're going to, if we just have a 1 MeV neutron source, we're going to have 0, 0, and then 1 MeV will have like a spike, impulse, 0, 0. That's going to be our phase space for this guy here, if this was a 1 MeV or whatever, a point neutron source. So this is getting back to our main point here. This is a notation for a fission neutron source. And finally, we can have S subscript D, which is phase space of R and E. This is a delayed neutron source, which we'll get into much more when we get into reactor kinetics. And there's also other types. There's plenty of ways we can get neutrons in a reactor. Any sort of X in reaction, where X is some sort of incident particle. This is a neutron source type reaction. So for example, we could have the gamma in reaction, where a photon goes in and a neutron comes out, or we could have the N2N, or more rarely the N3N reaction. These are all, you can call these maybe neutron-controlled neutron sources. Neutron-controlled neutron source. Okay. So that's what I wanted to touch on today. We've gone over a bit of the formalism of neutron current, and a bit about the neutron sources. Next time, I'm hoping to give you a bit of intuition on the cross section before I go in further about the interpretation of flux.